Welcome back to the channel. I'm your host, and today we're diving deep into one of the most fundamental algorithms in machine learning, gradient descent. Did you know that gradient descent is the backbone of almost every machine learning model you've ever heard of? From neural networks to linear regression, this algorithm is quietly working behind the scenes to make AI possible. In today's video, we'll explore what gradient descent is, how it works, see it in action with Python code, and understand why it's so crucial for training machine learning models. So, grab your coffee, hit that subscribe button, and let's get started. Imagine you're standing on a mountain in thick fog and you want to reach the bottom as quickly as possible. You can't see the entire landscape, but you can feel the slope beneath your feet. Gradient descent works exactly like this. It's an optimization algorithm that finds the minimum value of a function. In our case, the cost function of a machine learning model. Mathematically, gradient descent uses calculus to find the steepest descent direction. The gradient tells us which way is uphill, so we go in the opposite direction to go downhill, towards the minimum. The key insight is this. We start with random parameters, calculate how wrong our model is using a cost function, then adjust our parameters to reduce that error. We repeat this process thousands of times until we reach the optimal solution. Let's break down exactly how gradient descent trains a model. There are 4 main steps that repeat in a loop. Step 1, forward pass. We make predictions with our current parameters. Step 2, calculate cost. We measure how wrong our predictions are using a cost function. Step 3, calculate gradients. We find the slope of the cost function with respect to each parameter. Step 4, update parameters. We adjust our parameters in the direction that reduces the cost. As we repeat this process, our cost decreases and our model becomes more accurate. It's like rolling a ball down a hill. It naturally finds the lowest point. Gradient descent isn't just used in one algorithm. It's everywhere. Let me show you some popular examples. In linear regression, gradient descent finds the best line through our data points by minimizing the mean squared error. In neural networks, it's used in backpropagation to adjust millions of weights and biases across multiple layers. Logistic regression uses it to find the optimal decision boundary for classification problems. Even support vector machines can use gradient descent variants to find the optimal hyperplane. The beauty is that the core concept remains the same. We're always trying to minimize some cost function. Now, let's get our hands dirty with some Python code. I'll show you how to implement gradient descent from scratch for linear regression. First, let's import our libraries and create some sample data. Now, let's implement the gradient descent algorithm. The learning rate is arguably the most important hyperparameter in gradient descent. It controls how big steps we take toward the minimum. If the learning rate is too small, our algorithm will take forever to converge, like taking baby steps down a mountain. If it's too large, we might overshoot the minimum and never converge, like taking giant leaps and jumping over the valley. And if it's just right, we get smooth, fast convergence to the optimal solution. The key is finding that sweet spot, often through experimentation or adaptive methods. As models get deeper and more complex, we encounter 2 major problems: vanishing and exploding gradients. Vanishing gradients happen when the gradients become extremely small as they propagate backward through the network. The early layers barely learn because their gradients are almost zero. This happens because we multiply many small numbers together during backpropagation, and the product becomes tiny. Exploding gradients are the opposite problem. The gradients become huge and cause wild, unstable updates to our parameters. Fortunately, we have solutions: gradient clipping for exploding gradients, and techniques like batch normalization and residual connections for vanishing gradients. Standard gradient descent has some limitations, so researchers have developed several improved variants. Let me show you the most important ones. First, we have different batch sizes. Batch gradient descent uses all data points, slow but stable. Stochastic gradient descent uses one data point at a time, fast but noisy. Mini batch gradient descent uses small batches, best of both worlds. Momentum helps us build velocity in consistent directions and dampens oscillations. Atom combines momentum with adaptive learning rates for each parameter. It's like having a smart autopilot for your optimization. Let's be honest about gradient descent. Here are the main advantages. Simple to understand and implement, works well for convex functions, memory efficient for large datasets, and foundation for most ML algorithms. But it also has some disadvantages. Can get stuck in local minima, sensitive to learning rate choice, can be slow to converge, and struggles with different parameter scales. The key is understanding these trade-offs and choosing the right variant for your problem. Now here's where things get really interesting. I've created an interactive demo that shows exactly what we've been talking about with learning rates. Let's start with the learning rate that's too small, 0.001. Watch what happens when I click this button. See that? The progress bar barely moves. This represents what happens in real gradient descent. The algorithm takes tiny steps and needs thousands of iterations to make any meaningful progress. It's like trying to walk down a mountain taking baby steps. You'll get there eventually, but it's going to take forever. Now let's try the optimal learning rate, 0.01. This is our Goldilocks zone. Perfect! Look how smoothly and quickly it converges. The progress bar fills up completely in just a couple of seconds. This represents efficient learning. We're taking appropriately sized steps that get us to the minimum quickly without overshooting. And finally, let's see what happens when our learning rate is too large, 1.0. This is where things get chaotic. Yikes! Look at that wild oscillation. The algorithm is taking such huge steps that it keeps jumping over the minimum point. It's like trying to run down a mountain so fast that you can't stop at the bottom. You just keep bouncing back and forth. This interactive demo perfectly illustrates why choosing the right learning rate is so crucial. Too small and you're wasting time, too large and you'll never converge. The key is finding that sweet spot in the middle. And the best part, you can try this at home. The code is right here on the screen. I encourage you to download it and experiment with different learning rates yourself. Before we wrap up, here are some pro tips for using gradient descent effectively. 1. Always normalize your features. It helps gradient descent converge faster. 2. Use learning rate scheduling. Start high and gradually decrease. 3. Monitor your cost function. It should generally decrease over time. 4. Try different optimizers. Atom is often a good starting point. 5. Use early stopping to prevent overfitting. And that's gradient descent in a nutshell. We've covered everything from the basic concept to advanced variants and practical tips. Remember, gradient descent is like rolling a ball down a hill to find the lowest point. It's the engine that powers machine learning, helping our models learn from data by continuously improving their parameters. If you found this video helpful, please give it a thumbs up and subscribe for more machine learning content. Drop a comment below if you have any questions. I read and respond to every single one. Next, we'll dive into momentum-based gradient optimizer. Thanks for watching, and I'll see you in the next video.